Hello everyone. As I mentioned in my previous video on timers, one of the things that I used in that timer video was interrupts and interrupt service routine, or ISR. So I want to explain the interrupts a little bit more with details and show you a demo of interrupts here with a PIR sensor that I just published a video on it and a push button here. So let's get started. And some of the material here are coming from our textbook as well as this website here. Okay. So what is an interrupt? An interrupt is something that tells the microprocessor or the brain that, hey, I need to do something right now. Okay. So give your processing power to me for a second. Let me take care of this thing that needs immediate attention. And they could be triggered by a hardware or a software setting. So there are hardware interrupts and software interrupts. Okay, so as the name said, it interrupts the flow of the code momentarily to get something done that needs immediate attention. And then it goes back to the rest of the code. So the hardware ones are the ones that detect something changed over some pin. Okay, you can do it with hardware timers too, like we saw with timer 0, 1, and 2, with keyboards or anything. So if they need immediate attention because some signal on a hardware changed, because a key is pressed, because something happened, these are the hardware interrupts, and we're going to see how to use them. And software ones are the ones that you typically use timers and you or some other methods, mostly timers, to basically through software and without any hardware changes, you put the time into the processing power into a temporary interrupt. I show you one example that it was with overflow or compare mode, CTC, of timers. That is what we use a software interrupt. So here we're going to see both. But first, the hardware interrupt, know that in general, the C++ itself does not provide direct interruption handling mechanisms, but if you use it with a hardware like Arduino embedded systems, then there are functions for that. So if we want to do hardware, for instance, on a pin, if the signal is rising from low to high, we want to do something, correct? That is a hardware interrupt. So here, anytime the signal on a specific pin, in this case pin number 2, goes from low to high, so it's a rising edge, whenever this happens on that pin number 2, we want the counter to count up. So this could be very good for counting pulses, right? So if you want to count pulses, anytime there is a rising edge, if you count it, you can count the number of pulses. So you can use this, for instance, if you want to count basically, if you have an encoder or optocoupler and you want to count the number of pulses, which gives you an indication of the angle rotated. So in rotary encoders, you can do that. So here you see that first we have this function called interrupt service routine, or ISR. This is the function that will be activated and will be executed when an interrupt happens. Okay, this is an important topic and we have seen it in timers video. So what does this function do? Anytime that this function is, anytime that interrupt is called, all this function does, it changes the variable count by 1. It increases, it made that number go up by 1. And initially you started with 0, and this guy make it go up by 1. Now one thing I need to talk to you about it right here is, although this count variable looks like it is inside this increment function, ISR function, but I can change it, okay? And it's also defined outside the function. These variables that are defined outside any function, including the ISR function, including the loop or setup, these variables are called global variables. We define them outside any function, and for that reason, any function in your code will have access to it and they can change it. So this ISR can directly go ahead and change it. This guy can show it, it can change it, or anything. Okay, so these are the global variables that all functions have access to. And you're going to see more of that when I show you my code here. you can see that there is a lot more than that. So we do not have only one of that, we have a lot more than that. In this case, I have this motion detected is a global variable, this button pressed is a global variable, okay? But this debounce delay, that is, or this current millis is a local variable. This variable is only defined within this ISR function, so it can only be accessed here and modified here. But these guys that are defined outside the functions, these four, they can be accessed anywhere and changed anywhere. These are global variables, unless you say it's a constant. If you say it's a constant, you are not supposed to change that. But if they are just variables like these three, guess what? You can change them. Okay, so these three are global variables. Okay, so going back, look how I get the hardware. So what I do is, first I say, do the serial communication. Why? Because I want to show that count variable. I say go to pin mode 2 and make it an input with pull up, so you don't need an external resistor. It uses the internal resistor for it. So read the signal from pin 2, and then what would you do? You attach an interrupt. This is the function used for external interrupts. You attach an interrupt to what? Digital pin to interrupt 2. You say the pin I connect my interrupt to is pin 2. What function would be called whenever something happens on this pin? The increment function. So you pass to it the ISR function. And what condition causes that interrupt to be activated? Rising. You see, the rising edge. So digital pin to interrupt pin number, the ISR function, and the condition. If you provide these, then that's all you need to do. So now your system constantly monitors pin 2, and as soon as it sees a rising edge, it is going to call the increment function. And what does this function do? It adds 1 to the count, and the loop, all it does, takes that count variable and show it with some delay. Okay? So you see, this is as simple as that. Now you can change this pin 2 to other pins and look at what they are doing. So, a few things I need to talk about. One was the function, attach interrupt, and this is the syntax for it. The pin, the function, and the mode. Now, what kind of modes, what kind of conditions do you have? There are 4 conditions. Low, change, rising, and falling. Rising and falling are rising edge and falling edge. But low is low, so if you're low, it is going to send an interrupt activation whenever it's low. It doesn't look at whether it's changing or not. And change doesn't care. So both of these for change will work, whether rising edge or falling edge. If you go high to low or low to high, both of them counts for the change. Okay, so there are all 4 scenarios that you can do. Now, another important thing is attach interrupt. Remember, we have to connect it to some pin, correct? We have to use digital pin to interrupt. The question is, as I said, you can use other pins. Now, can you use all of the pins on Arduino? No. When you use digital pin interrupt 2, there are only really 2 pins in Arduino that you can monitor, and those are pin 2 and pin 3. And the external interrupts for them are called int0 and int1. So pay attention. If you want to monitor pin 8 attached to an Arduino, the pin 8 of Arduino, you cannot use this kind of function, attach interrupt. It is not going to work. It only works for pin 2 and 3. So what if I need more than that? I need to monitor pin 8 or pin 10 or something. Is there anything I can do? Yes. There is another type of interrupt that I'm going to show you how to use that. But this function only works for pins 2 and 3. Now, one thing I need to talk about are the volatile variable. These are, I mentioned them in one of my previous videos, but I mentioned them again. These are variables that when your computer, or Arduino in this case, stores them, these are typically, first of all, used with ISR functions. And since interrupt can happen at any time, and these variables can change any time, you are saying to the compiler that, hey, don't do any optimization for storing these variables and accessing them. Just put them somewhere. I might need them anytime. Don't do any compiler optimization for putting them in the memory and reading them. Okay, just they are volatile, they can change any time. And typically, as I said, we use them for variables that are changed by the ISRs. So you can see here that if I go to my code and show you these two variables, motion detected and button pressed, that are changed within these two ISR functions, you see that I have defined them as volatile. Okay, that means they can change, don't do any optimization for them. So these were the simple hardware interrupts that we had on pins 2 and 3 with attach interrupt command. What are the other types of interrupt that you have available in like Arduino? The other one that I said are software interrupts. These are the ones that you typically use a timer or something, and there is no pin directly to activate the interrupt. So how would you use that? I have shown you in the timer, but let's look at another example. So here you're using this flag variable that is going to change within my ISR. So you see it's a Boolean operator. I started with false and I set it as volatile. Now in the setup, I use my communication. First thing I do, I disable all the interrupts, and this is a good practice, we'll talk about it, no interrupts. So I set all of these variables to 0, and then I start setting up my timer interrupt. So you see that I'm using timer number 1, first of all, you see they are all 1. Then I'm running in CTC mode. How do I know? This wave generation mode 1, 2 variable, I'm setting it to 1, so that is CTC mode for timer 1. And then I'm comparing my counter to what kind of number before I reset it. I'm counting only to 15,600. Remember, timer 1 is 16-bit, and that TCNT variable, correct? That number 1 in this case, that can go up to 65,000 something, correct? So here I'm counting about a fourth of that because I want to reset my timer a little bit faster. And I'm turning both of these 2 bits into 1, so I'm using a pre-scaler of 1024 here. And I'm turning this compared to A mode on, so I'm clearly enabling the timer compare interrupt. Then, once I did all of my setting, I'm going to activate all the interrupts globally again. So these 2 commands are doing the exact opposite of each other. Okay, now that the interrupts are all set, it is time to define the interrupt service routine. And since it's a timer and not attached to any pin, and it's from timer 1 in comparison mode, all we need is to call the interrupt for it, which if you looked at my previous video, the interrupt for that one is timer 1 comp A vect. That's all you need to do, and that one will look at the timer for counter 1. As soon as it reaches this value of OCR1A, it is going to go to inside of this function, and inside of this function what you do, you set that flag to true, and true corresponds to the interrupt has occurred. So in your loop, anytime the flag is a true, you're going to say, hey, timer interrupt triggered. And once that happens, you're going to reset the flag back, so it goes for the next basically interrupt and get ready to be changed back to true and show it. Okay, so this is your interrupt service routine, timer 1 comp A. Now if you use the B one, it just becomes comp B. If you use the overflow one, then you use the one for overflow. Okay, and I'm gonna show you right now what are the timer ISRs that you have. For timer 0, if you just go with regular overflow, so you count from 0 to 255, and then overflow happens and interrupts is activated, the ISR is this guy, timer 0 underscore OBF underscore vect. Okay? But if it's comparison mode, CTC mode, then you have comp A and comp B vect. For timer 1 is similar, except it's timer 1, comp A and comp B and OVF. Now, timer 1 has one extra thing, and that is capped vec, okay, which is for input capture interrupt. If you remember, when I talked about the timer in my previous video, said that one of the specific things that you have was ICP, input basically capture, right? And what this one does, if some specific event occurs on some specific pin, in this case pin 8, then this one can capture the time of that event. So the TCNT1, the variable, the counter variable for timer 1, can be saved if the input on pin 8 basically experiences a specific event. So you see, if you want to look at pin 8, what you can do is you can look at this interrupt and you can capture even the time of it. But is that the only one? So for instance, if I want to monitor pin 9 or pin A0 or A2 or stuff like that, what can I do? I'll show you those ones as well. And for timer 2, you see the interrupts are very, very similar to timer 0. Okay, so timer 1 has 4 interrupts. Timer 0 and 2, they have 3 interrupts. Okay, so these were the interrupts that you had for different timers. And I also showed you the external interrupts on pins 2 and 3, as we talked about, which you use by attach interrupt. Now, before I move on and show you the rest of the interrupts that are available, there is one thing I want to talk about, and that is this command here, this no interrupt that we use in the beginning. What is that? Why did we have to do it? Because you see that first, I deactivated or disabled all of the interrupts, then I put them back on. Why do I have to even do that, right? Why would you use a no interrupt early on in the code, on the very top? So there are 3 reasons to use the no interrupt early on in the code. One, which is, I would say the most important one, is called atomic operation. So what is atomic operation? Some operations are atomic. What does atomic mean? It means that they have to be completed without any interruption, because it can, for instance, change data integrity. So these operations should be done without any interruption happening. Before these operations are ended, no interruption should happen. Otherwise, the data that they will give you is going to be ruined, right? You're going to lose the integrity of your data. If that's the case, you need to first deactivate all the interrupts, then put all of your atomic operations, and then what? Once they are done, go ahead and enable all the interrupts back again. Okay, so right after disabling them and before enabling them, you have to put your atomic operations here. Otherwise, the interrupts that start to happen will affect their data. And similar things is, for instance, we have called critical initialization. What is this? Some hardware peripherals also, when you want to set them up, you have to make sure there is no interruption happens. Otherwise, again, they cannot be correctly initialized. So they should also go right between these 2 commands. So not only the atomic operations should fall inside this, but also the critical initializations. The ones that should not be interrupted as well, they should go over there as well. And the last one is called preventing basically inconsistent state. What is that? So most of the time during the setup, and you see this part of the code is the setup part of the code, during the setups you might have some states that are inconsistent. You don't know whether they are in one state or the other, whether they are high or low or anything. When you disable the interrupts, you make sure that these inconsistent states are not affected by the interrupts, and so you can settle them down before doing anything else. Okay, so you are avoiding any inconsistent states by first disabling the interrupts, doing whatever you need to do, setting up all the states. Okay, you can see here. And then once they are settled, then go ahead and activate them. So here you get basically all of the setups for states that might be not necessarily super consistent. So just wanted to mention this before I move on. So what else do I have as interrupt in an Arduino? One next category is called external interrupt. So what is that one? So these are for pins 2 and 3. And as I said, they have their own dedicated interrupt vector. What does it mean? Means you can individually monitor pins 2 and 3, and if anything happens on these pins 2 and 3, then you know what happened to them, and you can individually activate an interrupt. Well, that's exactly the same thing as I mentioned earlier. Remember I said int 0 and int 1? That is exactly what you had up there, so it's nothing new. That's that very same thing that you do with attach interrupts. But there is another category. These are called pin change interrupts. As opposed to individual pin being monitored, its value, whether it's changing, rising edge, falling edge, or anything, now you can have a group of pins together, okay? And all of these group of pins, they share a single interrupt for all of them. For instance, all pins 0 to 8 or 8 to 13 or A0 to A5, they all share a single interrupt and a single monitor. And when the value on them is changing, then some interrupt will basically be activated. So it says that, hey, somewhere between pins A0 to A5, something happened, some value changed. Okay, so they share a single interrupt. Now, how do you know which one of them? Because it could be any one of them. That's where there is another category that is within the group, and that will tell you which one it is. Okay, and I'm going to show you that later in a second when I want to talk about pin change interrupt control. Okay, I'll show you how to use this PC int 0, 1, and 2, which I just mentioned here. I show you how to use this PC int 0, 1, and 2 vectors to basically specifically know what pin was basically, I would say the value on what pin has changed. But just remember that pins 8 to 13, they share the same vector, int 0. Pins A0 to A5, the analog ones, they have PC int 1, and pins 0 to 7, they have PC int 2. So literally there is one interrupt for any pin in Arduino, but some of them they have individual interrupt, some of them they have a share interrupt. But again, within that share interrupt, if you want, you can tell which one of them, and I'll show you that in a second. But let me summarize one more time these two important commands that I told you, the interrupt and the no interrupt. Or in some other versions of code, you might see psi and cli or cli. Okay? So these two are the same command, these two are the same commands literally for our applications. The first one enables the interrupts globally. Okay, so when you say psi and you don't need to pass to it any argument, just psi, open parentheses and close it, that activates and enables all of your interrupts at the high level. And psi, if you want to know what psi stands for, it's set interrupt enable. And CLI or CLI means clear interrupt enable. That will disable all of the interrupts globally. Okay? So these are two important commands that you see I have used in this code right above, right? So here you see I have used no interrupt and interrupt, but if I wanted to, I could have used the CLI and SCI. So instead of this one, I could just say CLI, and instead of this one, I could just say SEI. That's the same thing. Now, if they are the same thing, why do I have two versions of it, right? The matter of fact is they are not exactly the same. There is a small difference between them, not for our applications, but if you want to know the difference, the SCI one is basically it's a function that any AVR microprocessor or microcontroller developed by the Atmel company can use it. So it's not just for Arduino Uno. If you want to use other microcontrollers developed by Atmel in the AVR category, they are all using SCI. But the Arduino one is interrupts. So if you are using Arduino, just use interrupts. But if you have some other microcontroller, AVR by Atmel, you can use SCI in all of them, including Arduino. The same thing goes for CLI and the non-interrupt. Non-interrupt is Arduino only. This one is for all of those types of processors or microcontrollers. Okay, so I guess I talked about attach interrupt in the past. I showed you how to attach an interrupt to a specific pin and call the function for it and with what mode. But if you want to release that pin so it's not monitored anymore, if you want to free that pin, how would you release the interrupt, remove the interrupt from it? The command opposite of attach interrupt is called detach interrupt. And all you need is to tell it what pin. And that is going to remove the interrupt from that pin. Okay, continuing, for the timers that you have, the timer controls, remember that when you set up a timer, there are three major variables that you have to determine. For instance, here for timer 1, especially in CTC mode, you have to tell it what mode you are acting on. Is it the normal mode? Is it the CTC mode? Is it the PWM mode? That is determined by this wave generation variable. Then if you want to set prescaler, then you have to use the CS bits to determine that. And then to enable it or not to enable it, you have to use this variable here, OCIE, and set this variable time, timsk. Okay? So timsk here, which stands for timer interrupt mask register, this is the one that enables or disables a specific timer interrupt. So for instance, if you say set OCIE1 to 1 bit, set it to 1, that means activate timer 1 interrupt, but for what kind of operation? For comparison, match A. If you use B instead of that, now it will be comparison match B. If you wanted to do overflow, then use another one, and if you forgot which one, as I said, you can always go back and look at my timer video. And you see in the timer, if I go down and show you, look here. Let me go down a little bit more. Here we go, look. So these are for timer 0, but if you want, you can change them. So you see OCIE 0A and 0B, or 1A and 1B, or XA and XB, these are for compare match. Now for overflow, it's TOIE 0, right? So if I use TOIE, instead of these, instead of that, I say what? 1, and then TOIE and 1, because it's timer 1. That means what? That means enable timer 1 regular overflow interrupt. So this time, you're not going to count to a specific number and compare. You're just going to go and count to the maximum number of that, which was 65,000 something. Okay, so with this one, with this register, you can enable any of those modes. Okay, good. Now, one thing I need to talk about is The next type of interrupt register that we have is called TIFF-RX, and this X is again the timer mode. So for timer 1 is TIFF-R1, for timer 0 is TIFF-R0. This TIFF-R, which stands for Timer Interrupt Flag Register, this is a flag, this is a Boolean operator, variable, that determines the status of the timer interrupt. So whether your timer interrupt has been activated or not, okay? And this register has a bunch of bits. The 4 major bits of this are ICF, or Input Capture Flag, OCF, A and OCF B, that 1 again is because it's timer 1, output compare match A, match B flag, and then TOV1, which is overflow flag. So it has 4 different flags, and depending on which one of them has been activated, that flag will go to 1, the rest of it will stay at 0. For instance, in here, when you are doing compare A interrupt, whenever you count to that number, whatever that number is, the OCR one, whenever you reach that, this guy is going to go to 1, the other ones will not be affected, because you are comparing with A. If I do this case, where you are allowing it to go to its max, then this guy will go to 1. If you are comparing the B, match B, this one goes to 1. And if you want to capture the time, remember, this is the time that some event happens, this guy goes to 1. Okay, so it has 4 specific bits, and this OCF one that you see here in this code, this is just one of the bits instead of TR1. So what kind of meaning does this part of the code have? If I have a code like that, what does that mean? It means if any interrupt has been activated, and that one is for comparison with A, then do something, correct? That means you overflow and you reach the variable that you set up. In this case, if you go back and look, that variable I set up for timer 1A is this number. So anytime your TCNT1 reaches from 0 to this number, and 1 overflow happens at that number, not at 65,000, this variable here, as I said, this guy goes to 1. So both of them are going to be 1, and so now you can basically do something, whatever that you want. For instance, display, hey, I reached 15,000 counters, and I'm resetting it back to 0. Or again, do something, like turn some LED after that. Okay, so let's move on to a few other things, and then I'm going to show you an example, or a few examples actually. So the next thing I want to talk about is, remember I just said that we have some groups of pins that we can monitor them all together, and then if we want, we can know which one within the group has been basically triggered, right? Which pin, the value of it has changed. So remember, we said that we have this 3 interrupts, these guys, which are shared by several pins. So I'm going to explain that part now, the pin change interrupts. So let's go and talk about the pin change interrupts. So what do we have? So there are 2 things here. One is called PC ICR, which is Pin Change Interrupt Control Register. Okay? So this is the one that if you want to know specifically which pin group is being triggered, you can use that. So here you say, hey, the value of PCIe0 set to 1, okay? What does that mean? It means, hey, I want to monitor pins 8 to 13, which is called group 0, so that 0 here is referring to group 0, not timer anymore. I want to monitor pin 8 to 13, any of them that shows any change in variable in the value of the pin, of the voltage applied to the pin, go ahead and basically inform me or activate some interrupt. Okay? Now how do I know which pin is which group? So group 0 or PCIe 0, as you can see here, that is group 0, and that means pins 8, 9, 10, 11, 12, 13, as well as 14, AR, EF, and SS. If it's PCIe 1, that means pins A1 all the way to A5. If it's PCIe 2, those are pins 0 to 7. So you see, the way I refer to this group of pins is with these three variables. And if I set any of them to 1, means only monitor that group. Yes? So this is how I monitor the entire group. Now, how do I monitor once this group is activated, is triggered, how do I know which one of them? So between 8 to 13, which one of them received the high voltage or the low voltage or rising edge or falling edge? How do I know that? This is with the second variable called PCM-SKX. Again, this X could be 0, 1, 2. This is the pin change mask register, and that one will tell you which pin. So here, once PCIe 0 is 1, that means, hey, monitor group 1, which is 8 to 13. Then if you look at these pins, 8 to 13, there are only 7 of them, right? So there are 7 pins here. How do I know which one of these 7 pins, right? And of course, this guy too. Out of these, I need to refer to this variable now, PCInt 0 to 7, and each one of them corresponds to one of these. Similarly, if I look at PCInt 8 to 14, right, then each one of them refers to one of these pins, and 16 to 23. So I can read that specific pin group, and I can look at the specific bit, and that will tell me which one of the pins is activated. Okay? So I can clarify this if I go through an example. So let's say I want to monitor pin 8, right? And I also want to monitor pin A0. How do I do that? So if I want to monitor pin 8, pin 8 belongs to this group, PCInt 0 to 7, and it belongs to PCIe 0. So the first thing I do, I say, hey, PCIe 0 is 1. That means I need to monitor this group. On the top of that, with an OR, I say also activate PCIe 1 for me. Why? Because I want to monitor A0, and A0 belongs to this group. So I say monitor both of these groups for me now. Then which pin among this first group? Pin number 8. And pin 8 is the first one, is PCInt 0. So look, I say PCInt 0 is 1. That means pin 8. If I had to use pin 10 instead of pin 8, what should I use here? If this one was supposed to be pin 10 instead, what should I change that? You're right, because 8 is 0, 9 is 1, 10 is 2. So if I said PCInt 2, that means monitor pin 10. But since it's 0, I say that's 8. And what about A0? Well, as I said, A0 is the first pin in this group, and the first pin corresponds to 8. So you see, I say PCIn 8 is 1. That means pin A0. So running these three lines together means, hey, monitor these groups, but not all of them, only pin 8 and pin A0. Anything happens on them, go ahead and activate some interrupts for me. Now, how do you activate the interrupt? I'll show you that one as well in the bottom code, but I just want you to know how to refer to these specific pins. Now here, let's say I want to do something. What is it that I want to do? I want to monitor pin 8, and anytime the voltage on it changes, I want to toggle an LED when something changes on pin 8. Okay? How can I do that? in my setup, I say put pin 8 to input pull-up. So first I read the data from it and I use a pull-up, so I don't need to use an external resistor. And then the LED as an output. Now look, I say go to the first group, so pins 0 to 8, right? And then read the first bit, which is pin 8. So by setting these two values for PC ICR and PC MSK 0, that means only monitor pin 8 for me. Now activate all of the interrupts. Now look at the function for your interrupt. Look, I say ISR PC INT0 vect digital write to the LED pin, the digital read of it with the NOT. Remember I told you in previous video that means if it's high, change it to low. If it's low, change it to high. So that's a toggling, right? Just reversing whatever it is. If it's on, make it off. If it's off, make it on. So whenever something changes on pin 8, go ahead and basically toggle the LED. Now, if instead of this, it was pin A0 that you were monitoring, how would you change this code? Pin A0 belongs to the group 1, belongs to this group, correct? It belongs to this one. The timer that you have to use for it is this guy. And it's the first pin, so it's 8. So what you need to do in this code, if you had to do it with A0, monitoring A0, is this one should be 1 instead of 0. This guy should be 0, but this one should be 1. So group 1, pin 0 of it, that means monitor A0. And anything happens on A0, toggle the LED. Yes? So this is how you use the interrupts for groups of pins and specific pin. Now, one fundamental question before we finally look at the circuit here and the LED example. You might say, why didn't you do it with attach interrupt? Remember, with attach interrupt, I can monitor a specific pin and see if the values on it go up and down, or rising edge or falling edge. Why didn't you do it with attach interrupt and you have to go through these pin change interrupts? The thing is, if you remember, the attach interrupt, the external ones, only work for pins 2 and 3. Anything other than pin 2 and 3 cannot be monitored by attach interrupt command, right? Let's go back. These guys, as I told you several times, only and only work for pin 2 and 3. Any other pin, if you want to monitor, you have to use what? The pin change interrupt. You have to use this table. Okay? And this way, you can now monitor anything that you want. Good? And let me add one extra thing for you as a bonus. So remember, when we are using external detections, right? External pins, we are allowed to have different modes. We can detect low, change, rising, or falling on pins 2 and 3. What about these group pins? For these, can we have all of those modes as well? The answer is no. All you can fill is a change. There is no rising mode, falling mode, or low mode. The only thing with these guys that you can basically detect is a change on that pin, not a direction. Okay, so these are not as powerful as those external ones with attach interrupt. So this is one last thing I wanted to tell you. Finally, let's look at the code here. So what is this code? What is this circuit? So in this code, I have combined the motion sensor that I had with the PIR, right? And I added an extra component here, which is this push button. Let me maximize this so you can see better. So my PIR sensor is here. And as soon as it detects anything, it turns the LED on and doesn't turn it back off. So the LED goes on and stays on. And in order to turn the LED back to off, I have to press on the push button. Okay, so here the motion will trigger it on, and then the pressing the push button will put the LED back to off. So let's see how it works. So like my previous video, the first thing I do, I allow 30 seconds just to calibrate the sensor. Once it's done and the sensor is attached to pin number 2, because remember pins 2 and 3 I can directly look at hardware changes, and that's what I did for the push button and the PIR, because I want to see them in real time. Once that 30 seconds pass, it shows sensor is active, so now it is ready for detecting any motion. So I put my hand in front of it, okay, and let's see, seems like still it is not there yet, or there we go. Yeah, one of my pins were loose, so I moved my hand and it turned on. Now look, if I bring my hand back again, it's not going to do anything, okay? It's not going to turn it off again. Remember in my previous video, after so much time and not detecting a motion, it went off, right? But not this time. Right now, it might not detect any motion anymore, but my LED is not going to go off. Because if you look at my ISR for the pure sensor, all I'm doing, I'm setting this flag motion detected to true. And then in my code, whenever this motion detected is true, what does it do? It is going to send a high to the LED pin. Okay? It is going to do that. So this LED is going to go on. Now it is going to turn the motion detected back to false. But when it makes it false, what's going to happen? If it makes it false, is that going to turn the LED off? No, because you see, when is it that the LED goes off? Whenever it receives the push button. When the push button pressed is on or 1 or true, that is when it is going to go off. Not when this motion detected goes back to false, it goes to off. And this part, like previous code, is just to basically write everything one time and wait a little bit time for it to go off and so on. So this part is like my PIR sensor video. This part is the same. All I changed was to add a push button here and use interrupts. Now you see that the 2 interrupts I'm using are on basically pin number 2 and 3. And those are external interrupts here, right? So we have button ISR and motion ISR here. And I did not use any other interrupt, as you can see, but if I wanted to, I can add a timer here, right? And do that. Well, kind of I have a timer here, but without any interrupt. Because when I use function millis, millis is using timer number 0. So I am using a timer, but I'm not using the interrupt version of timer 0. So if you want, you can change this millis part and change it to something that is using one of these interrupts, right, of timer 0. So you could use, for instance, this one if you wanted. And anytime it overflows, you do something. But the time that it takes to count from 0 to 255, it is very fast. And I want to take a few milliseconds or more before I do anything. That's why if you want to do that, then you have to count how many times you overflow and do that. And that is already done in function millis. If you watch my timer video, you see that's exactly what millis is doing. It's 64 times overflowing and then skipping the 65th time. So here is a simple demo. That is my circuit here. And hopefully this video was useful to you. See you in the next video.